So this is my fourth talk. I'm Michael Pilquist, if you don't know me. I maintain a bunch of open source Scala stuff, and I work at Comcast. We build video systems, and we use Scala to do like a bunch of soft real-time type streaming stuff. So if you want to talk to me about that, come find me later. This is my shortest time slot I've had at this conference. Normally I get like an hour. This year I have like a half an hour, so I thought I'd pick something really easy to talk about so they can fit into 30 minutes. So I picked polymorphic effect types and concurrency. Because I thought, that would definitely not be a challenge. All right, so let's talk. About a year ago, I stood here and I had promised at the time that we were going to release FS2 0.10 and Cat's Effect 0.9 at the time. And it turned out it didn't make it. We didn't have those releases out in time for the conference, so we had like release candidate builds instead, right? And getting those releases over the hurdle, if you will, took us until January 2018. So in January 2018, we had this type class hierarchy on the left part of the slide there. The stuff in green is from Cat's core. The stuff in blue is from Cat's effect. And it was a pretty simple type class hierarchy, maybe too simple, right? We talked a little bit last year. I think John had a talk last year where we talked about like fiber-based concurrency and how do we do concurrency with that particular type class hierarchy. And the answer was that downstream libraries really had to re-implement their own notions of concurrency using those particular type classes. So fast forward about 9 months. 9 months of debate and discussion and lots of perspectives from a lot of different parts of the overall Scala open source ecosystem. And we ended up here. And I want to point out this is like 1.0, right? So there's some long-term stability. There's more boxes, so clearly it's better, right, than 0.10 or 0.8. But in no way is this necessarily where it ends, right? We're committed to long-term stability on this particular type class hierarchy, but you'll probably see a Cat's effect 2 that looks a lot different than this, right? As we continue to understand what it means to abstract over effect types. All right, so what are we talking about? Really today, what I want to look at is two things. One is principled and polymorphic resource management, right? I want to be able to write code as a library author or even perhaps as an application developer in one of my systems that doesn't bind to a specific effect type or a specific effect type plus some transformer stack. Instead, I want to do that polymorphically in my effect, but still have these very crisp abstractions that I can depend on, I can rely upon, and I have guaranteed behaviors. So anyway, we have this new bracket type class. It's near the top of the hierarchy right now. It extends directly from monad error, and it gives us this crisp definition of resource management. We'll see a bunch of this today, and we'll look at all these in quite a bit of depth. The other thing I want to talk about is the concurrent type class. It's kind of the same idea. Right? We want to be able to do concurrency. We want to be able to do sort of these lightweight threads. Kind of be able to start things and reason about them and cancel them. And again, do that in a way that's portable, that's crisp, that's very dependable, regardless of what particular effect type or transformer stack we might stick into our programs. Okay. There's a bunch of other stuff in Cat's effect, so we're going to be talking a little bit about the concurrent package. We're going to spend some time on both refs and deferreds today. And then there's a bunch of other stuff. What notably we're not going to be talking about is the IO data type or the sync IO data type, which is another one of our effect types, especially useful if you're working in Scala.js. So if you do want to talk about those, come find me later. But this is really more about the polymorphic capabilities provided by this library. OK, let's look at the concurrent type class. So if you take the concurrent type class from Cat's effect and distill it down to sort of its essence, right, this is what we have. We have a type class concurrent. It's polymorphic in some effect type F. It extends this async type constructor, or type class. We don't really have to get into that too much. The important thing really here is the start operation. So if I have a program called FA of type F of A, I can start it up sort of asynchronously, still do this in a completely referentially transparent way, and then get back a handle to that thing that I started. Okay? So we call these handles fibers. You can sort of think of them like threads. They're not mapped to real operating system threads by any stretch of the imagination. And sort of the key operation on these fibers is this join. So joining on one of these handles lets us sort of block, right, on the response, on that particular program finishing with a single value of type A. Okay? But we're not literally going to block. We're not going to block a thread, right? We want to sort of register a callback, sort of. So a good way to think about this is like if you've used Scala, util concurrent future, I'm sure all of us have. If we want to write a computation that's sort of dependent on a previous future, right? We're going to use flat map, right? And so same thing here. We're going to use that very same pattern that we're used to from like using futures. We're going to be able to call join and flat map on this f of a that comes back to represent sort of like this dependency, this sort of like block for a value of type A, but do it in a way that's not actually like holding an operating system resource, not actually holding a thread, right? Very similar, by the way, to like Go routines or Node.js or like any of the other sort of like callback-based sequential concurrent systems. The other important operation on Fiber is cancel. So cancellation is sort of this difficult thing to implement ad hoc after the fact. And like John had a talk last year about that. So fibers support cancellation. So any f of a, any polymorphic effect that we want to be able to start up, we have the ability to request cancellation. You can see cancel returns this cancel token. It's really just an alias for an f of unit. And we'll look at a bunch of examples of both join and cancel in a moment. But first, I want to try to implement this particular operation. So just to be clear, this operation comes built in. It comes from cat's core. There's a parallel type class. If you have the right imports, you can just call par-tupled on two like IOs or two sort of arbitrary effect types, and you get this particular operation. But it's really illustrative, I think, to implement this and sort of get a feel for what it's like working with fibers. Okay? So what's par-tupled? Well, it's basically given two programs, one that computes an f of a, or one that computes an a in an f context, right? And one that's an f of b. Give me back a program that sort of runs those two, computes those two a's and b's, and sticks them to a tuple, combines them, right? But unlike like a normal tupled operation, we want f of a and f of b to run in parallel, right? We want them concurrently executing, and when the last one finishes, give us back that return tuple. So the question is, how can we do this in a again, in this very crisp way, right? Depending only on the abstractions that are guaranteed to us by our type classes. And like, here's a way to do it. It feels pretty natural. We import some syntax so we can call the type class methods directly on values. We can say fa.start to go start a fiber up to compute a, right? We call fb.start to go start a fiber up to compute b. We then wait for the a value to come out of that first fiber by joining on it, wait on b, and then yield our tuple. Right? Very similar to like code with Scala util concurrent future. Now, unfortunately, this is incorrect. This code actually has quite a bit of issues with it, but it will work. If you try this and do a couple sample programs, everything appears to be working. So what happens when we run this particular program? So imagine our f of a argument fails with an exception. In this case, it sort of just fails immediately with a runtime exception. And we have some arbitrary f of b. Right? So let's think through our implementation. What's going to happen at runtime? We start up f of a. So now concurrently, something's going to go out and start computing the a. Right? And that's going to fail sort of concurrently. It's not going to fail right away. So we do get back a fiber a. We hold on to that fiber a. We then go and kick off fiber b. Right? We run the f of b program, get a fiber to it. Now that's off and executing. So now let's use our types. We see fiber a.join gives us a value of type a. But we know our fa program just throws an exception, right? So there's no way we can just sort of conjure up this a, right, out of thin air. So we know from the types that flat map on join cannot complete, right? Or rather, that a value is never going to be bound to a value of type a. So what happens? Well, so overall what's going to happen is our f of this AB tuple that comes back is going to fail with this propagated runtime exception, right? It's just going to like propagate up the stack, the monadic stack here. But what happens to fiber B? right? So if it fails, that's cool. Like, the exception propagates out, but we're often running this f of b program, right? And so in this case, we're leaking this fiber that we started up, right? And it's not the only leak in this case. Because we have fiber cancellation, like someone could actually start up the overall returned program in a fiber and let it run for a little bit and then cancel that. In which case, we might leak both fiber A and fiber B in this case, right? All right, so how do we fix? This is a pretty mechanical refactoring in this particular case, where we sort of upgrade what we're doing and how we're binding on these fibers. So in this case, we're using the bracket operation. So brackets coming from the bracket type class, it's sort of the top of the cat's effect type class hierarchy, and concurrent certainly extends bracket. So the trick here is we're going to treat the fibers as resources, sort of like as an operating system file handle or like a socket we've opened, right? We've started up a fiber, we want to treat it as a resource, and no matter how we terminate, we want to make sure those fibers get cleaned up. So basically all we're doing, if you look at sort of the mechanical refactoring here, is we replaced our flat map calls with calls to bracket. Now bracket takes two argument lists. It takes, the first argument list looks like flat map, like an A to F of B. The second argument list is like a cleanup routine, right? So no matter how we terminate, whether it's normal termination, like we've computed the value, whether it's termination due to an exception or termination due to a cancellation, we're guaranteed to have this cancel operation get called. So anyway, in this case, we have we replaced two flat maps. We just called join, and we called the built-in tupled method to just synchronously sequence two programs. Okay? So this is a pretty common refactoring of replacing a flat map with a bracket to add cleanup logic. Okay, let's talk about refs. So a ref is the cat's effect version of a Java util concurrent atomic reference. Or another way to put this, if you've never used atomic reference, it's like the cat's effect version of a var, right? So we do all this stuff to do all this cool FP stuff, and then we're literally going to use vars in some of these programs. But we're still going to do it in a referentially transparent way. We're not going to give up on our functional programming principles. So what does a ref look like? It's polymorphic in effects F and a value type A. It has two main methods, get and set. So you can imagine if we're talking about a replacement for a var, get and set are the two main operations, right? So the return type of get is not A, but rather F of A, right? It's a program that when we evaluate, we get the current value out of this ref. Set just takes a pure A, gives us back an action, an F of unit, that when we evaluate that F of unit is going to set a value into that ref. Okay? That's an important distinction there. And then there's some more interesting operations, maybe some more fundamental operations in the case of this access thing. The access thing is kind of interesting. It's an operation if we call, we get a program that gives us a snapshot of the current value of this var. Right? It gives us a snapshot of the A, whatever's currently there, along with a way to replace it with a new value. So that's kind of heady, but we're going to use that in a moment. And then some lower level derived operations. I want to point out that construction of a ref is effectful. I can't just new a ref. Okay? So the ref companion object here has this of method. Its return is an F of ref FA. Okay? So our ref itself, the construction of it is suspended in our effect type. And so why? Why can't we just new a ref, right? And the answer comes down to substitutability under program meaning changes under substitutability. If I have two expressions in my program, both of them have the exact same call to ref.of. If I replace those two expressions with one expression, my program meaning is going to change, right? Because I had two variables, and now I have one variable, one sort of memory cell to put values. All right, really simple example. This is just a toy example. We can call ref.of. We have to specify an effect type. In this case, I use a concrete one, IO, and I initialize it to the value 2. Refs must always be initialized to a value. They are never uninitialized, right? Just like a var, excluding nulls. And then we flat map into it, right? We flat map into this make. You can sort of think of what comes back there as this constructor that every time we flat map into is going to create us a new memory cell, right? A new ref. In this case, we update the current value to 5 times the value. We call get, and you get back 10, like you'd expect. Now, if instead we had flat mapped into make twice, we would have created 2 different memory cells right? And would have gotten back different values. All right, so how might we use this stuff to do something interesting? So this is a use case from an application a colleague of mine was working on. It's a Scala JS application. It uses React. There's a bunch of UI events coming from the browser, and they need to be debounced, right? So if we get a bunch of the same event type back to back to back, we want to take action only on the most recent event type. So we sort of want to, like, when an event comes in, kind of delay it for a little bit of time. If we don't see any other events of that same type come in, then sort of dispatch it out and go and do whatever it does. And so this is what we had come up with, this debouncer class. So we have two operations, apply and cancel. Cancel, you can imagine, is going to be called like if you leave the screen, right? If like the overall React component sort of unmounted, taken out of the browser, we're going to shut down this debouncing. So the real main operation is apply. Apply is given a program f of a, and returns us back a program of f of a. So we're going to change the behavior, though, of f of a. What we're going to do is first delay it, right? So just kind of just slow down the execution of it for a moment. And then as long as no other new program comes in, cool, right? We'll let it evaluate. And then we'll return the overall value in the returned f of a. Now, if another new t comes in, though, while it's waiting, we want to cancel that thing and then never complete it. Just let it hang. So if any code had flat mapped on it, it's just never going to see one of these a's come out. All right, here's how we might implement it. And remember, we want to do this like pure functionally, right, using all of the principles that we typically would use. So here's how we do it. We, in this case, have this current val we're going to put on this class. It's going to be a ref. And the ref now, we need to pick like what our value type of the ref is. What are we going to store in this memory cell? Right? So this is pretty standard of like our concurrent state is going to be in a ref, and then that ref is going to be stored as a field on a class. All right. So in this case, we're going to store a cancellation token for the last task that we queued up, right? Or we went off and start to execute. So our cancellation tokens are f of units. And in this case, we have an option of f of unit to represent the initial state where we haven't actually started up yet. Let's implement cancel first, because it's pretty straightforward. Cancel we'll implement by using the modify combinator on refs. So modify, you pass a function to it. It gives you the current value of the ref. You return back a new replacement value, along with sort of a side channel return. Okay. So in this case, we're going to say modify the current cancellation token. Whatever C is the current cancellation token, replace it with a none. Get rid of it. But then also sort of return that C on the right-hand side as just like a side channel return. And that side channel return is going to be like the overall result of binding into our modify. Okay. Now, since we get this f of unit now, like if we flat map into this overall expression, we're going to get this f of unit representing our cancellation token, or actually an option f of unit. We want to go and execute it to actually cause the execution to occur, to actually do the cancellation. So in this case, we're using sequence underscore. It's just a syntax trick. It's a combinator, right? But basically, it has the effect of saying if this thing's a none, it does nothing. And if this thing is a sum, it's going to execute it. Okay? In this particular case. All right, that's it for cancel. So that's thread safe. It's resource safe. Cancel is good to go. Apply is a little more interesting. Apply, we're going to use this access operation. So access is kind of mind-bending. We call access. We flat map into it. And we get a tuple. The first element of the tuple is a snapshot of the current value of the ref. In this case, I call it cancel. And the second element of the tuple is a setter, right? That lets us attempt to set the ref to a new value. Now, that might fail. And I have to handle that if it fails. Right? And it would fail like if there was concurrent updates occurring. Right? So if in between the time that I called access to the time I evaluated my set, if something else came in and like concurrently set my ref, my overall setter is going to fail. All right, so what are we going to do? Well, the first thing we want to do is cancel the old cancellation token. Get rid of it. Right? Run the task to cancel that old f of a that we were running. The next thing we want to do is delay execution of the new program t. Okay, so here we're using delay and right shark and t, right, to say, wait a certain period of time, but do it in a non-blocking way, like don't block a thread, right? And after that finishes, like delay followed by, go and do the original program t. right, so where did delay come from? We define that as a val. That val we really just called the sleep operation using an implicitly available timer in the effect type f. So timer is from cat's effect. It's one of our built-in data structures that lets us either work with delayed time, like in this case of using sleep, or working with like clock values if we wanted to read the current clock of the machine. All right, so first we're going to cancel the old token. Now we're going to delay the new program. Now we don't want to just run it now, though. We want to start it up as a fiber. And again, we're going to treat this fiber as a resource. So if we're canceled or otherwise fail, we have no situation where we leak that resource. So we start it. We call bracket. We've got to now do something with the started up delayed program. But if for any reason the body, where we currently have these question marks, if any reason that body fails, we cancel the overall returned fiber. All right, so what do we do inside of bracket? Well, the general idea is we just want to store off the cancellation token for the thing we stored up, you started up, right? It'll be the new value of the ref. So we can call try set, right? So try set, the thing that access gave to us as a function. So we call try set. And I said that might fail, though, right? So we have to handle the case that it fails. Or we could ignore it, but we want to make this correct, right? So we handle the case where it fails. In order to do that, we flat map into the return try set. We get the flag saying whether or not we were successful or not. And here's where it's sort of interesting. If we were successful, we can just join our fiber now. Like basically just say the returned f of a that we're going to return, just return the overall result of that delayed program. If we fail, on the other hand, what that means is someone else has concurrently updated our ref with a new task, right? Like there's a race condition, someone replaced our current value with another task, in which case we would just want to immediately cancel the thing that we tried to start up, right? And then hang. This is what that concurrent f.never does. Hang and don't return a value. OK? So anyway, we do use this exact code to debounce Scala.js events from browsers. OK, one other main data type. We have this deferred thing. So deferred used to be called promise. It's very similar, in fact, to promise. We renamed it because we didn't want to confuse folks, because there's a little bit of a difference between a deferred value and a promise. Deferreds have two operations, get and complete. So again, it's polymorphic in F and A. If we call get, we get back a program that returns us an A. But now, unlike ref, right, because ref had a get operation like this, unlike ref, a deferred operation is initialized without a value, right? And it represents an eventual completion with a single value of type A. All right, so if we call get and then flat map into that, you can imagine our program is going to, in some way, semantically block, right, until that new A is available. So again, this is sort of just like flat mapping on a future. Now, complete's interesting. You call complete, you pass it a pure value A. It gives you an f of unit. You evaluate that f of unit, and it has the effect of completing this deferred value with that value. So anyway, it looks really, really much like a promise. Why didn't we call it promise? It's because we don't do an error channel here. There's no way to complete a deferred with an error. And the implication of that is that get itself can't actually fail with an error, right? It makes it a little bit simpler to both implement and reason about, at least arguably. If you do want to push an error channel through a deferred value, you just wrap it at either. Right? All right, so my use case for this is implementing a queue. So what I want to do is implement sort of a naive queue. It's going to be unbounded, but it's going to be completely pure, completely referentially transparent, and it's going to be both resource safe and concurrent, thread safe, right? Completely thread safe and totally concurrent. All right, so signature-wise, it sort of looks like deferred. We're going to have almost like, in this case, set and get, right? We're going to have it in queue operations. So it's given a single value of A, giving back a program that sticks that A into a first in, first out queue. And then I'll have a dequeue operation that just says, get me the next value out of the queue. Okay? And our challenge is to implement this using the existing data types we've already created. All right, we're going to use the same pattern. We're going to store our concurrent state inside of a ref. That ref is going to be stored as a val in a class, or in this case, a constructor argument. Now the type that we're sticking the value position here is kind of mind-bending when you first look at it, or at least it's large, right? So the type is an either. So the state of our queue is going to be one of two cases, right? Either we have a bunch of elements already in the queue sitting there waiting for someone to come pick them up. In that case, we're going to represent that as a write. Okay? And so our write here is going to be a Scala collection immutable queue of type A. They're just sitting there waiting for people to dequeue them, right? Now, the flip side is we might not have any elements, but instead we have people waiting for elements to show up, right? We're going to represent that as a left. And our left, we're going to also use Scala collection immutable queue, but we're going to have a queue of these deferred values, these promises for future elements. All right? All right, so how would we then implement this? Let's do enqueue first. The enqueue operation is given a value of type A. We're going to use this modify operation on our ref. And we're going to do this side channel return again, right? So when we call modify, we're going to be given the current value. We're going to return a replacement value as well as a sort of a side channel output, right? And now in these cases, our side channel output is going to be another effectful value, which we're immediately going to go and execute. So update the ref to a new value, and then execute some action as a result of that update after it's been successful. This is so common, there should probably be a combinator for it. It's intentional that there's not. If you want to know more, come talk to me. I'm happy to debate that. But OK, so let's take a look at how modify is implemented. If we have a new element coming in, and we already have a bunch of elements sitting in memory, this is easy, right? In that case, we can just take this new element A and stick it onto the end of our current queue of elements. And so we update our state with a new write, just with that A, appended to the end. Now, we don't want to actually have to do any effect in this case, so we just use unit.pure to say, don't do anything after this completes. If the state's a left instead, well, there's a couple things we have to handle, just to handle like empty queues and whatnot. But the general idea is take the head element out of this list of waiters and complete it with the new element that came in. And now if we're left to nobody else waiting, we're going to update the queue to be back on the right-hand side with an empty set of elements. If we do have folks waiting, then update the queue to still be on the left-hand side with one less waiter. Okay? And that's all this does. Now, the side channel here, we return this ws.head.complete. Right? So we turn an action that when we flatten in a moment, that's going to have the effect of having the dequeued element wake up one of these listeners. All right, let's look at dequeue real quick. Dequeued, we're going to create these listeners. Right? We're going to go and allocate these listeners. So in this case, we're using the apply method on the deferred companion object. We say create a promise, right, for this value fa. We flat map into that, right, because a construction is effectful. So we flat map into that. Now we have some waiter w, right, something that we can give out or wait on. And now we want to register that w in the state of our queue. We're going to look at what that looks like. We're going to use that side channel return pattern again. So after we call modify, we're going to flatten in this case, right, to execute some value that we return. And then finally, we're going to wait for that deferred value to show up. The w.get call is going to give us an f of a. We have an f of a in the final position inside of a flat map. So you can imagine overall we get an f of a as a result. Okay? All right. The two cases here, again, there's some just nonsense to deal with the edge cases. But like if the queue already has elements in it, the general idea, we check for the empty, but the general idea here is highlighted. We want to immediately complete the brand newly constructed waiter right away with this value. Okay? And then on the left-hand side, if we have waiters in the queue already, we're just going to queue up this new waiter to the end of it, and we have no action to take in that case. Okay? So this call to w.get is interesting. So we did like all this work, and then we wait. And we started one of the more complicated examples today by talking about cancellation, like the par-tuple example, right? We had cancellation. We had a problem where we leaked that fiber, right, upon cancellation. Well, it turns out in this case, we actually have a memory leak. It's kind of a gnarly little memory leak. And so the general idea is like what happens if an exception occurs or if cancellation occurs. In this case, it's really cancellation. We know it's not an exception, right, because I said deferreds can't fail. W.get can't fail. But someone could call dequeue, give it some time, and if an element doesn't show up, cancel that dequeue, right? So the common operation there is a timed dequeue. Like dequeue an element, but if I don't have anything after 1 second, notify me with a timeout, right? And the way that's implemented is with fiber cancellation. All right, so why do we have a memory leak? Well, when cancellation occurs, we're going to come off this w.get, but the state of our queue class still has this w sitting around, right? That w is still up in that ref. And so now imagine like your system has a lot of events coming in, a lot of folks dequeuing events, but you have some of them start to time out. What it's going to look like is a lot of your events are getting eaten by the queue. Like some of them might be making it out, right? But these outstanding w's that are never looked at again, it's going to look like the queue's sort of, dropping these events on the floor. All right, so how can we fix? We're going to use our same trick as earlier, right? We're going to place a flat map with a bracket, right? And the trick in this case is we're going to treat our resource as our deferred value. The deferred value is the thing that we're going to try to, keep a handle on. Okay, so we replace flat map with bracket, and now we have to implement a cancellation clause to say if for whatever reason we come out of this block, right, out of this use block, what do we need to do to clean up the state of our queue to handle the fact that like W is no longer going to be waited on? Now it may not be there, right? The cancellation might have occurred before W ever got put into the state, or the cancellation might have occurred after W got, w.get got completed. So anyway, our cancellation basically has to handle all of those cases. In this case, we just do like a linear walk through the waiters in the queue and just remove the one that we're going to return, or that we created in this case. There are more efficient ways to do this. I'm not going to go through all the more efficient ways to do this, but there's a bunch of other ways. This is a bit of a naive implementation of a queue, but hopefully that gives you like an idea of the way these combinators can sort of build bigger and bigger concurrent data structures off of some pretty simple primitives. Right? We're not going to do semaphores today. We don't have time. But if you are interested in semaphores, like the slides are online and the full implementation's there. Also, there's a dining philosophers implementation. It's a bit of a challenge to see if we could do it. I posted today, so if you want to see what dining philosophers would look like with FS2, it uses semaphore. And so semaphore in Cat's effect is actually implemented one way, but we used to implement it with deferred and refs internally. Like semaphore was a derived data structure off of these more simple concurrent data structures. All right, so that's Cat's effect 1. It's pretty much what I wanted to go through today. If you use any of these libraries, like FS2, Doobie, HTTP4S, they're all built on this infrastructure of Cat's effect. And all of these data types up here, the Cat's effect IO, Monix, and ZIO types, all of them have Cat's effect instances. You can pick and choose whatever one you like the best, use it in your applications, and all of these techniques are completely safe, completely concurrent, and all completely principled. All right, so that's all I had. I think I have time for for 1 or 2 questions. All right, Paul. Yeah, so the question was, what's next for Cat's effect in general, I'd say. So one, like I mentioned before, the type class hierarchy is not final in any stretch of the imagination. One of the strengths of Cat's effect, I think, is that you have a ton of diverse opinion on how functional Scala should evolve. And we continue to kind of take everybody's feedback and evolve the library in a way that maybe we all didn't foresee a year ago. Right? And I think you'll continue to see that occur. That might entail things like a type class to represent effect types that can express errors, like unfailing I/O types. Maybe we go and do like the whole bifunctor I/O that like John's been pioneering in ZIO. Maybe there's type classes to represent that. I think you'll see those types of things. At the same time, I think we'll continue to see Cat's effect concurrent data structures get built. We were talking earlier about like maybe some type of pooling data structure to handle like connection pools and object pools and things like that. So yeah, I think you'll see both. Overall, Cat's effect, how has sort of like two primary purposes. One is this interoperability layer, right? One is so like we can work on things like Doobie and not make a choice of an effect type for all of the users of Doobie, right? But another is to provide parametricity and provide the ability to write in a tagless final style in our applications and get all the benefits that we see in our libraries, but get them at the application level as well. So I think you'll see innovation on sort of both of those fronts. Any other questions? All right, thanks all.